Hi guys, how's everyone? I hope all of you are doing fine and are ready to another session of learning. So, let me welcome you to Graph Theory with Ma'am P. Yes, that's me. So, for this session, let us recap uh, basic concepts about graph theory. So, let's start with the graph. So, here is a sample of a graph. There. A graph is a representation of vertices and edges, wherein vertices are the nodes or these dots here, and edges are also called sides. So the lines here connecting our vertices. So this is an example of a graph. So graphs are similar with numbers, wherein we we represent numbers by using symbols, and here in graphs we represent the group of vertices and edges as illustrations. So, aren't you wondering? We know for a fact that we have operations on numbers, right? Addition, subtraction, multiplication, and division. So, how about graphs? How do we operate them? Okay, so for this session, I'll be presenting you results of a study entitled Graph Operations on the Commuting Graphs of Symmetric Groups. This study was done by yours truly and my undergraduate advisor, thesis advisor, Professor Rolando G. Panopio. So this study uh, mainly focused on the properties of the graphs resulting from performing graph operations on the symmetric groups, on the commuting graphs of symmetric groups. So first, let us know what is a commuting graph of S sub n or the symmetric groups. So these are graphs with vertex set S sub n minus z of S sub n, wherein z of S sub n is our center of the symmetric group. So if we would recall, symmetric groups are uh, consist consist of n letters, so permutations of n letters. Okay, and here in the commuting graph of symmetric groups, we just get the elements of S sub n minus its center, wherein the center is always trivial, which is also its identity element. Okay, so there are two distinct vertices, say x and y. It is connected, or they are connected by an edge if and only if x star y is equal to y star x, or they commute. That's why we call it commuting graph of S sub n. So we're in the star here is the operation on the permutations in S sub n. So the number of its vertices of gamma of S sub n is given by this expression, which is n factorial minus 1. And the number of edges of the commuting graph of S sub n is given by this expression. So we have here the square of n factorial minus 1 minus the summation of the difference between n factorial minus 1 minus d of a all over 2, wherein a is an element of S sub n. So for illustration, let us look at the graph or the commuting graph of S sub 3. So we have here uh, the number of vertices is 5. So we have here vertex 1, 2, 3, 1, 3, 2, 1, 2, 1, 3, and 2, 3. And there is only one edge, the edge connecting the vertices 1, 2, 3, and 1, 3, 2. Okay, so obviously it follows from these formulas. So these formulas are from the study of Laius way back 2012. So another illustration is the graph earlier. So you remember this graph? So this is the commuting graph of S sub 4. So wherein we have 23 vertices. So all those nodes are 23. And the number of edges, so these lines are 22. Okay. So now let us look at the different graph operations we are going to perform on these commuting graphs of symmetric groups. So we have 7 famous graph operations done in this study, namely join, disjoint union, disjunction, box product, cross product, box cross product, and complete product. But in this video, I will only be discussing 3 graph operations from those 7. So such as join, disjoint union, and the complete product. So for the join of two graphs, G and H, so we have here G plus H. It is the graph with the vertex set, the union of the vertex sets of the two graphs, and its edge set is given by this expression. So for example, we have here a graph G containing vertices 0, 1, and 2, and we have edges 0, 1, and 1, 2. If we get the join of this graph G with our graph H, which has vertices AB and the edge AB, we will have this resulting graph, G plus H. Okay, now applying this operation on the commuting graphs of symmetric groups. So we have here propositions regarding the properties of the resulting graphs after performing join on the commuting graphs of symmetric groups. So for the first proposition, we have here the degree of a vertex and the number of edges is also given here. Then there is a remark that the join of two symmetric graphs is connected but not complete. So let us look at the resulting graph. So remember S sub 3 or the gamma of S sub 3, commuting graph of S sub 3, and this one, the commuting graph of S sub 4. If we get the join of these two commuting graphs of symmetric groups, it results to this big graph here. So using the propositions earlier, we have here the number of vertices of the commuting graphs of S sub 3 and S sub 4 is 28, and the number of edges is 138, while the degree of a vertex, here I just picked one vertex, 1, 2, 3 sub 1, so this vertex here, and the number of uh, edges connected to it, or that is what we call degree, is 24. So for the next operation, we have this joint union. So this joint union of two graphs G and H, so we have G union H, is the graph with a vertex set, which is the union of the vertex sets of the two graphs, and each its edge set is just the union of the edge sets of the original two graphs. So basically, if you have this graph G and this graph H, you are just combining them. No further additional edges nor additional vertices, but you just combine the two. So that is a disjoint union. So applying this joint union or getting this joint union of commuting graphs of symmetric groups, come up with this proposition. So the number of edges is just the number of edges of the first graph plus the number of edges of the second graph, which is obvious from the definition. So we have here different remarks. So the number of vertices is just the same with the join. So if you remember this symbol, the plus sign. And disjoint union of two graphs is not connected and not complete. So let us look at what happened to two commuting graphs of symmetric groups when we perform disjoint union. So here we have gamma of S sub 3 and gamma of S sub 4, and this is their disjoint union. Okay. So looking at their properties, so we have here the number of vertices is the same from the joint, which is 28. The number of edges is 23. Okay. Since we have 22 edges from the gamma of S sub 4 and 1 edge from the gamma of S sub 3. Then the degree of this vertex, so we have here 1, 2, 3, 1, 2, 3, 4, sub 2 is 4. This one. And for the last operation, which is complete product or G star H, so it is a graph with this vertex set. So the cross product of the vertex set from the first graph and the vertex set from the second graph. And the edges are made by following these relationships. Okay, so we're in GH comes from uh, the first graph, and G prime H prime comes from the second graph. So here we have graph G and graph H again. So their complete product looks like this. So there are many edges here resulting and from applying complete product. So as compared to the other two operations earlier. So let us look at how complete product is applied on the commuting graph of symmetric groups. So I have here a proposition for all VW. So this is the new form of the vertex and the complete product of two commuting graphs of symmetric groups. So this is the degree of one vertex here. And the number of edges is given by this long expression here. So we're in, again, this V of gamma sub 1 is just the vertex, the number of vertices in the first graph, while this is a number of edges in the second graph, and so on. Another proposition that we've proved is that the complete product of the commuting graphs of symmetric groups is connected if both the first and the second commuting graphs are connected. And also, the complete product, though it is called the complete product of two commuting graphs, is not complete. So let us look at the result of applying complete product on two S sub 3s. Okay, so I picked S sub 3s, two S sub 3s instead of an S sub 3 and an S sub 4 because as what you've seen in the definition here, you'll be getting the cross product of the vertex sets of the two graphs. So S sub 3 and S sub 4 is a lot to handle. So I've just get that two commuting graphs of S sub 3s. So this results to this beautiful graph here. So using the propositions earlier, which we have proven in the study, the number of vertices here is 25, since the number of vertices in the commuting graph of S sub 3 is 5, so 5 times 5 is 25. Then the number of edges, surprisingly, is 280. And let us look at this certain vertex here, 1, 2, 3 sub 1, 1, 2, 3 sub 2. So this is the vertex. Okay, so its degree is 18. So the number of edges connected to it is 18. And there you go. So for references, so I have here 5 for studies and a textbook um, authored by Hungerford. And I hope you've learned something about graph operations and especially in the commuting graphs of symmetric groups. If you have questions, you can email me at ptbulaklak@up.edu.ph. And thank you for listening. Goodbye. Take care.